And I brought a problem that actually goes way back. The time that I first started learning about it was when I really first started doing these math circles more than 10 years ago. I just recently started thinking about it a lot again and came up with a lot of new ideas that I hadn't seen before, and then I started doing it with some different groups of kids, and they came up with some new ideas that I hadn't seen before. So let me just explain the problem, and then I'll give you a chance to experiment some and see what we can come up with, and we'll see where it goes from there. So we'll start with a square, but you could really start with any regular polygon you want. You can start with a triangle or a pentagon or whatever, but squares turn out to be pretty interesting. And we pick some numbers to put on the corners. What would you guys pick? 7. 7. 7. And what would you like?
4.
4. Okay. And how about in the back? You want to pick one?
No.
No?
Do you want to pick a number? Pick a number.
Can you pick one for us? What do you want to pick here?
3. No.
I don't know.
Just pick a number.
What's your favorite?
Pick a number and say.
5.
5, okay. And what would you like?
Is that 51 down?
Nope.
16.
16, okay. So then what we do is we're going to go to the middle of each side, like this. And we're going to put the differences. So let's see, up here, what do we put? 3. And over here, what do I put?
1.
Yeah, some people might think we should put -1 if we're going clockwise, but we're going to always put positives. No negatives allowed today. Okay, now between 5 and 16. 11. And 16 and 7. 9. And then look, the 4 new dots we made make another square. And we do it again. So let's see, what do I put here?
6.
6. And how about here?
2.
2.
10.
10.
2.
2. Okay, now I'll let you keep going and find out what happens, and maybe try some different numbers and find out what happens, and try some different numbers and find out what happens. And if you notice any interesting patterns in what's going on, then let's talk about them.
Can I use more paper?
I need more paper. Sure. So what happens? Anybody notice anything yet?
You always get down to the 0, 0, 0.
You always get down to 0? You tried every possible set of 4 numbers? I don't know. How many sets of 4 numbers have you tried so far?
2.
2 sets. Okay, so far it seems like if you keep going, zero, 4, 0, 4. Gets kind of hard to write in these small spaces, I guess. 4, 4, 4, 4. 0, 0, 0, 0. And I guess I kept going, 0 minus 0 is 0. So I could go for a long time if I wanted to be pretty boring. Yeah?
Also, if you set the four corner numbers to be infinity,
Infinity. I'm not sure that's a number or not, but okay.
well, like if the numbers never decrease to 0, then that pattern is not on forever.
Uh-huh. But what number should I start with for the pattern to go on forever?
There's no number that can start with that.
There's no number I can start with. Huh.
It has to end some point at 0.
It has to.
If the endpoints are finite.
Or finite.
Yes, if they're not, then
Are you sure? Like what if it's, 1, 2, a million, a billion or something?
This will end a billion circles later.
A billion circles later.
Lots of circles later.
Lots.
Lots of squares.
I guess what I'd like to find is, can you find something that lasts a really long time? Let's see, how long did this one last? I guess in one step I went to here, 2, 3, 4, 5, 6. So I'd say that these numbers, 4, 7, wait, how am I going to describe this? I'll start at the top left. 7, 4, 5, 16, 6 steps.
Pretty big square.
Draw a pretty big square. So I want to see somebody break the record what lasts more than 6 steps. Instead of erasing, you should probably save some of your work and try looking for patterns in what you've got. If you erase everything, then you won't be able to spot the patterns. So that's why I should all do method. Okay, so maybe let's try a slightly easier question that's still going to be related to this, which is, if all the corners start with 0 or 1, then what pattern lasts the longest? Because now we don't have infinitely many possibilities to try anymore, so it won't take as long to check them all.
Well, you can start from 0, 0, 0, 0 and work backwards.
Ooh. That's an interesting idea.
And if the level around 0, 0, 0, 0 is 0, 0, 0, 0, then
That doesn't really count, yeah.
So it has to be 1, 1, 1, 1.
Okay, so I have 0, 0, 0, 0 way down the middle. And the level before that would have to be 1, 1, 1, 1. Assuming we only have zeros and ones. Okay.
And the only way to get 1 is if you have a 0 and 1.
The only way to get a 1, if you're subtracting zeros and ones from each other, is for it to be a 0 and a 1. So it has to be 0, 1, 0, 1 before that.
So I guess you just keep working until you find that something repeats itself.
Just keep, well, if it repeats itself, then wouldn't that mean if we went forward, it would go on forever? That'd be good if we could find when it repeated itself. All right, so what's before 0, 1, 0, 1? I wonder if there might be more than one
I
choice.
think that decays in 3 steps.
Okay, hold on. So if we have
24, 24, 23.
0, 1, 0, 1, what could have come before that? Assuming we only have zeros and ones.
Then I have 0, 0, 1, 1.
Yeah, it could be.
From left and going
Starting from the left. Okay, so if we put a 0 here, then because of the difference of 0, that has to be a 0. Because of the difference of 1, these have to both be 1s. On the other hand, we could put a 1 here, but then we get the same thing, just flipped around, right?
Mm-hmm.
So assuming still that we only have 1s and zeros to work with, we don't really have two possibilities yet. These are really the same. So I'll just erase this one. Okay, so what comes before 1, 1, 0, 0, if anything?
You have a 0, 0,
Good
1,
one.
0.
Let's start in the top left.
Okay.
So this is 1, 1, 0, 0. So what could be up here in the top left corner?
1.
Could be a 1, or it could be a 0.
Right.
Right? If this is a 1, and I have a difference of 1,
That's 0.
has to be 0, and I have a difference of 0,
0.
has to be 0, and I have a difference of 0, has to be 0, and the difference of 1, so it checks, it goes all the way around. If I have a 0 here, then
1.
1.
1.
1, difference of 0,
1.
1, and difference of 1, so it checks again. So now it looks like I have two different solutions. It could have 3 zeros or 3 ones. Those look different to me, so maybe I need to worry a little bit now. How about before that? Is there anything that could come before that? Oh, I'm not going to crash. Again, it looks like I might have a whole bunch of possibilities, right? Because in this case, with the 1, 3 zeros, I could start with 1 on top or 0 on top. And in this case, I could start with a 1 on top or I could start with a 0 on top. So let's see, that's a 0, difference of 1, that's a 1, difference of 1, that's a 0, difference of 1, that's a 1. Wait a minute. Did I do that right? Look, this is 0, difference of 1 has to be a 1, difference of 1 has to be a 0, difference of 1 has to be a 1, difference is, but what happened?
The top can't be 0, has to be 1.
Top can't be 0, it has to be 1. Okay, so this is a 1, difference of 1, so this has to be 0, difference of 1, so this has to be 1, difference of 1, so this has to be
0. It doesn't work.
0, difference of 0, so this has to be
0.
0. 1
So
equals 0.
The case
Okay.
that goes longer is like 0,
Oh,
1, 1.
so try this one. Okay, so this is a 1, difference of 0, so this is a 1, difference of 0, so it's still a 1, difference of 0, so it's still a 1, difference of 1, uh-oh. 1 minus 1 does not equal 1. So that doesn't work. This didn't work, this didn't work, this didn't work. How about this one? 0, difference of 0, still 0, difference of 0, still 0, difference of 0, still 0. Difference of 1.
So that means that the case that lasts the longest is a 1, 0, 0, 0 or 1, 1, 1, 0.
Okay, so the answer is 1, 0, 0, 0 or 1, 1, 1, 1, 0. And how long does it last? Let's see. Lasts 1, 2, 3, 4, 5 steps?
No, first step.
No, the black one doesn't count, does it?
No.
The black one was wrong. Okay. 1, 2, 3, 4, only 4 steps, huh? Let's check. 1, 0, 0, 0. 1, 1, 0, 0. 0, 1, 0, 1. 1, 1, 1, 1. 0, 0, 0, 0. That's 1, 2, 3, 4 steps. Okay. So we solved that problem. So I guess what question should we ask next?
What if we have any possible? Is it 1, 0, 1, 2?
What if we allow 2s? Uh-oh. Now there's so many more things to try. Because even at the very first step, if we do this working backwards strategy, 0, 0, 0, 0, it could be 1, 1, 1, 1 before that, or it could be 2, 2, 2, 2. So we already have a couple possibilities even right at the very beginning. Whew. That could take some investigating.
Could be assigned variable.
Ooh, so you could try assigning variables, but the problem is that we're not really just subtracting. See, if we were really just subtracting, it'd be okay. A, B, C,
Right.
D,
But
and then we get
you have a whole bunch of absolute values.
absolute value signs, and those just become,
If we're working.
that just turns into basically an infinite-sized mess after not very long.
Right.
Not very infinite-sized, but really large anyway.
I mean, since we're working backwards, we're adding, right?
If we're working backwards, we're adding. Well, no, we don't know whether we're adding or subtracting is the problem. Let me give you an example. So let's say down in the middle we have 1, 1, 1, 1. Then I say, okay, what comes let's start with the 1 here. We don't know whether this should be 2 or 0. But there are only so many possibilities. This is a 2 or a 0, I don't know which. And this has to still be 1, assuming we only have 0, 1, and 2. And this has to be a 2 or a 0 again over here.
Wait.
If we only have 0, 1, and 2.
Is it like is it true that the ones in the top left corner and bottom right corner are always odds, and the other two are even?
If I start with an odd here, yeah.
If it's not, then it's flipped.
Then it's the other way around, yeah. So before 1, 1, 1, 1, it has to be 2 odds and 2 evens, and the odds and evens have to be opposite each other. That's definitely true. Maybe I should add that to our list of good ideas over here. Look at odds and evens. Seems like this is going to be pretty tough, though. Let's focus on this working backwards strategy a little more. Working backwards is a really good strategy. Really useful. Like, for example, what if we took this one that was 7, 4, 5, 16, and I wanted something that would last more than 6 steps? Maybe I should work backwards from there, right? Because if I can work backwards from there, then I'd break my record. I have something that lasts 7 steps. I don't think we've seen anything that lasts 7 steps yet, have we? Have we? Anybody have anything that lasts 7 or more steps? All right, I'm going to pass around a little handout with some ideas in case you get bored. And in the meantime, I'll let you think for a while about what we can do here. I guess, to me, the big goal right now is let's find something that at least lasts more than 6 steps if we can. Wow. Okay, so we just broke the record here. If, in the step before this, we had 1, that's a 7, so this might be an 8. That's a 4, so this could be a 12. I mean, these could also be other numbers, but that's a 5, so this could be a 17, and then we check the 16. It works. Okay, so we have our new record is 1, 8, 12, 17, 7 steps. That's good. How about the one before that then?
I'm not sure if there is.
Ooh. Not sure if there is. Well, let's.
There is, it's 10.
Oh, wait, slow down. I'm not ready yet. Okay, so what do you say comes before this?
10, 18.
Wait, where should the 10 go between which two numbers?
Top left.
Well, I didn't,
18, 8, and 1.
between the 8 and the 1. Okay. I see top left over there. I rotated my picture a little bit. 10 up here.
And
Okay.
then 18.
18, I'm good with that.
6.
Wait, then what goes down here?
6.
6,
And then 11.
11. Well, it almost works. You see the problem?
Um,
6 plus 11 is 17. But I need 6 minus 11, or 11 minus 6 to equal 17. Shucks.
Because if you let, like,
You know, I mean, let's just try to do it with some algebra, maybe, right? If this is, let's see, what do we have? 1, 8, 12, 17, okay. And
if you let the
top left,
yeah be
Let's-
A,
A.
and
Then the top right, what could it be?
A plus A or A minus A.
It's either A plus 8 or A minus 8. The two numbers have to be 8 apart. I don't know which.
A plus
How about this corner?
A plus 1 or A minus 1.
A plus 1 or A minus 1. This is where the absolute values get kind of painful to see all of the plus
And
or
then if you
minuses.
let the other part be B, then you have 4 pieces to consider.
Yeah. I was just going to kind of go from here, but that could go to A plus, let's see, plus another 12, that'd be A plus 20,
Or A minus 4.
or A minus 4, or from the other one,
A
A plus 4, or A minus 20.
And none of them work.
And none of them, if I go 17 away from here, I'm going to get a 16 or an 18, right? And here I have 4s and 20s, and here I have, can you not see because this big table is in the way? It's not a very movable table, so you can just slide it off to the side, I'm afraid. So I'll have to practice writing higher on the board, I guess. So anyway, the point is we have plus or minus 1 down here, and over here we have 4s or 20s, so I can see I can make like a 3 or a 5 or a 19 or a 3 or 5 or stuff like that, but not a 17. If I go 17 away from plus or minus 1, I can only get plus or minus 16 or 18, not 4 or 20. So there is nothing that comes before 1, 8, 12, 17. So much for the great working backwards strategy. But wait a minute. Is 1, 8, 12, 17 the only thing that comes before here, or is there other
Probably
choices?
not.
Can we come up with other things?
We can use variables again.
We could use variables again, if we like our algebra. Okay. So if I call this A, this could be A plus 7 or A minus 7. And this could be
A plus 16 or A minus 16.
A plus 16 or A minus 16. And then I have this 4 here. So this could be A plus 11 or A plus 3 or A minus 3 or A minus 11. And then how is that going to make a difference of 5? Well, the 3's aren't going to work, right? Because 3 plus 5 cannot equal 16. But 11 plus 5 can equal 16. So if this is A plus 11, this could be A plus 16. If this is A minus 11, this could be A minus 16.
Basically now we'll figure out is A.
So then I can pick A, In this case, we picked 1, but we could pick whatever number we want, like 43. And then this could be a plus 7, which would be 50, or it could be a minus 7, which would be 36. And then this would be 54 or 32, and this could be 59. That makes a difference of 16, that's good. Or 27, that makes a difference of 16, that's good. So we have a whole bunch of 7-step solutions. We pick A to be whatever we want. Then we decide whether we want to go A plus 7, A plus 11, A plus 16, and then the 16 will work. Or we go A minus 7, A minus 11, A minus 16, and the 16 will work again. So we pick any starting number here, and then we either go up or down 7, 4, and 5. And as long as we either keep going up or keep going down the whole way around, it'll work. But then 1, 8, 12, 17, that was kind of a dead end, right? There's nothing more that we can do to keep working backwards from there. But how about this one, or any of the infinitely many other choices? I mean, maybe the real question now is, without going through all that algebra, is there a way to tell which things are, I don't know what the word is for this, work backwardable? Is there a better word for work backwardable? Which are the things from which one can work backwards? That sounds fancier. So how can I tell? I mean, is there a way I can look at 1, 8, 12, 17 and say, oh, that's a dead end? And I can look at 43, 50, 54, 59 and figure out if it's a dead end or not.
Well, if you, well, basically you can think of it like an elevator with infinitely many floors, and you're going up and down.
I see.
And you have to get back to the same number after.
Ooh. So after I go all the way around the circle, so if I started, let's look at this one, for example. If I started with some number A at the beginning, then after I go 43, I'm going to be here at A plus or minus 43. Because I want either up or down 43 floors in my very tall building. Okay, and then what?
And then the last one would be.
Then I come to this 36, and I either have to go plus or minus 36, so the difference would be 36. So this number here has to be A plus or minus 43, and then that plus or minus 36. And then I go 32, and I have A plus or minus 43, plus or minus 36, plus or minus 32. So if I look at it in terms of the big square, if I had in my example 43, 36, 32, 27, and I start with some number A here, this has to be 43 away. It's either 43 more or 43 less. And this has to be 36 away from that. And this has to be 32 away from that. And then I have to come back to A again. So if I add or subtract, somehow I'm going up or down by 43, 36, 32, and 27, and in total I have to go nowhere. I have to come back to the same number I started with when I go all the way around. So how can I tell whether that's possible or not? With this one it works because if I did plus 7, plus 4, plus 5, and minus 16, that equals 0.
Well, obviously, you'd have to have an even number of odds and evens, because you want the parity to all end up being even.
See this, we have looked at odd even patterns. So what you're saying is, if it's work backwardable, then either they could be all even, or I could have 2 odds and 2 evens, or I could have 4 odds, But if I have 3 evens and an odd, then whenever I add or subtract them, I'm going to get an odd, and 0 is even, so that can't work. That makes sense. But this one has 2 evens and 2 odds, so
Right, but it doesn't always have to work. I mean,
if it doesn't have an even number of odds,
it's medium.
then it can't work. If it does have an even number of odds, we still don't know yet.
For example, 1, 8, 12, 17.
That's got 2 evens and 2 odds, but it didn't work.
Right.
Yeah. Well, what are the possible ways? If we have 4 numbers, and we have to add or subtract them and end up with 0.
You want to add the greatest and the least, and then subtract the
Yeah, so if I put them in order from least to greatest, like 1, 3, 6, 10, one way I could potentially get 0, if I'm going to add up 2 numbers, it has to be the biggest has to go with the smallest. Because if I did the 10 with any of these things, that would already be too much for the rest for sure. Because 10 is more than 6 and 3 is more than 1. So if I'm going to add up 2, it has to be in pairs like that. But here that doesn't work.
and it doesn't work on that.
But wait a minute, didn't we find that something went before 7, 4, 5, 16? And here it doesn't work. 4 plus 16 is 20 and 5 plus 7 is 12. But it did have something before it.
Oh, but now you can add the 7, 4, and 5, and then subtract.
So one possibility is to add them this way, but another possibility, if you're looking for what comes before it, is all 3 of the small ones together might add up to be the same as the one biggest one.
And it does.
And here it works. And in our 7, 4, 5, 16 example, it works.
But
So those are the only 2 possibilities, right? What could possibly balance the biggest one? Either it takes all 3 small ones to balance the biggest one, or the biggest one could be with the smallest one, and then the other 2 could balance it. So those are the only 2 possibilities to check. So if we want to check our 43, 36, 32, 27, first of all, the 3 smaller ones clearly add up to way too much for 43. So we just have to check whether 43 plus 27 is the same as 36 plus 32.
70 is not going to
That's not going to work. Yeah. So that one doesn't have anything that we can work backwards from either. But at least now we know what we're looking for. You see, we have all these choices. We could pick any number we want for A. Right? We pick any number we want for this A. Maybe I should be using more different letters of the alphabet. I can pick any number I want for this A, and I'm going to
So
have.
maybe 43 is just not right.
Maybe 43 was just not a good choice.
Right. So now we have.
So let's see. We have for our 4 numbers. If I look at the blue thing here, I have A plus 7, A plus 11, A plus 16. Or I have A plus, A minus 7, A minus 11, A minus 16.
So we can apply something and.
Oh, wait a minute, aren't those actually? Okay, fine. So we could try the same thing.
Doesn't
So-
seem to work for either one.
It doesn't seem that was quick. Let's in each case look at the biggest one. So there's 2 possibilities for each one. Either the biggest one adds up to all 3 put together, or the biggest and the smallest add up to the middle 2. And then I can check the same thing here. Either the biggest one equals all 3 of the little ones added up, or the biggest and smallest could add up to the middle 2. That looks like 4 possibilities to check. So let's check them. I could have A plus 16 equals A plus 7 plus A plus 11. Or I could have A plus 16 plus the smallest one, A, equals A plus 7 plus A plus 11. Or the same thing with minus. I could have A equals A minus 7 plus A minus 11 plus A minus 16. Or I could have A plus A minus 16 equals A minus 7 plus A minus 11.
Does A have to be an integer?
Well, that's a good question. I think we've been kind of assuming here that we're only using integers, but I suppose we could consider non-integers too. And I suppose we could always maybe, okay, anyway, we'll worry about that later. So let's look at these equations. here I can subtract a from both sides. I can subtract a from both sides, and I get 16 equals 18.
Nope.
That seems false. Okay, here I can subtract a from both sides, I can subtract a from both sides, and I have negative 16 equals negative 18. Okay, those were quick. Here I could subtract a from both sides.
2a equals 2.
I think I get 2a equals negative 2. So I have to subtract 18 from here. So I'm going to get negative 2 equals 2a. So a would have to be negative 1.
I thought.
I'm pretty sure we can't really get negative numbers here because when we're subtracting, I think we're taking absolute values, right? We're always picking a positive possibility. So a equals negative 1 isn't going to work. And how about this one? I could subtract a from both sides, and I could, don't I get some huge number for a? On this side I could get 2a, and I could move all those negatives over here.
2a, so a is 17.
Whoa, 7, 18 plus 16 is 34. So a is 17. A is 17, and then I have all these minuses. Okay, so wait a minute. We did all this algebra, but I'm not going to believe it until I actually see if it works.
Wait a minute. We didn't get the solution where a is 1, but a is 1 worked.
No.
Oh, sorry.
When a was 1, there was a dead end, and it couldn't be worked backwards
Right.
from. Yeah. Okay, so what this says is if we had, what do we have? 7, 4, 5, 16. Put that here. Then out of all the work backwardsing possibilities, we like the one where A, let's see which one was A. A is the one that goes where? Between the 7 and the 16, right? So A, we like the 17. And then we like the way where it went. A minus 7, so that was 10. Minus 4, so that's 6. Minus 5, so that's 1.
It works.
And so the question is, have we now made something that works? This was the only choice. We looked at all these equations and all these possibilities. The only possible one that we could keep working backwards from was this 1, 6, 10, 17. And then this one works. There's tons of solutions, right? We could, for example, if we just start with 0 here, and then 10, and then 16, and then 17, and then come back to 0, and it checks. But of course, there's other possibilities, right? I could start with 93 here, and then subtract and get 83 here, and then subtract and get 77 here, and then subtract and get 74. Wait, did I make a subtraction mistake? 76 here. And then it works. And so there's tons and tons of possibilities again, but most of them don't work for going backwards any further, right? They only work for going backwards further if either the biggest plus smallest equals the middle 2, or if the biggest equals all the smaller 3 added up.
7 plus 4 plus 5 is 16.
7 plus 4 plus 5 is 16, so that works. But how about here? Which green numbers should I pick if I want to keep working backwards? So we did break our record though, right? We found 17, 10, 6, 1. Let's see, where's my record breaking? I guess that's here. 17, 10, 6, 1, the last 8 steps. Because that's like a working backwards of one of these 7-step things. We picked the right one out of all these 7-step things. And we found we could work backwards one more step and get 8. Yes.
Do we do that again?
Yeah, let's do it again.
Until we get to it.
Let's do it forever. Let's do it. Let's do it. I want to find something that lasts, 100 steps. So let's just repeat this. We're up to 8, so you just have to do it maybe 90 more times or something. Hopefully before then we'll find some kind of pattern, right? That'll simplify things for us a little bit. Or we could write a computer program to check again. All right. Kind of want to save that thing that I just erased, so I'm going to write it down over here someplace. With zeros and ones. Okay. That was a good result too. Try all those things. Okay, so let's see. What do we have now? We've got 17, 10, 6, 1. So again, we're going to get these same equations, right? If we have, just like we had 16, well, let's look at what we get here. Where are we going to label our A? Maybe here?
Okay.
Okay. Maybe I should go with green so that it matches. A. This could be A plus or minus 10. This one is A plus or minus 17. And then for it to work, this one has to be A plus or minus 16 to fit between.
Wait, and or plus or minus 18 also.
It can't, because then it wouldn't work to the 10 and the 6.
Right.
Yeah, so it has to be 16.
So there are two solutions.
Just like last time. So we could have the biggest one, which is A plus 17, equals all the smaller ones added up. A plus 10 plus A plus 16. Or we could have the biggest and the smallest. But the biggest and the smallest is never going to work here because the biggest and the smallest will have a 17, whereas the two middle ones will have a 10 and a 16. And there's no way to combine the 10 and the 16 to make the 17. It'll be just like these, where the A's will all subtract out, and we'll have 17 equals 10 plus 16 and stuff. So those won't work. It has to be the biggest one equals all the other three added up. Because when you have two A's on each side, it's just not so easy to solve the equations because the A's all subtract out. It's not so good. But these equations have some hope, right? Here I could subtract A from both sides and do some more subtraction. I guess I get 1 equals 2A. So A would have to equal a half. And here I could subtract an A from both sides. And I get 2A equals 43. So A is 43 halves, or 21 and a half if you prefer. So it looks like I can keep working backwards as long as I'm willing to not have integers. And I guess I get two possibilities. A could be a half, and then with adding all the way around. Or A could be 21 and a half, and then with subtracting all the way around. So we have two more record breakers. Let's erase some of the scratchy, worky stuff in here. Broken record. 9 steps. Let's see, start with a half and go adding all the way around. 10 and a half. 16 and a half. 17 and a half. Or start with 21 and a half and go subtracting all the way around. 11 and a half, and minus 6, 5 and a half, and minus 1, 4 and a half. And let's check in each case. Wait a minute. Didn't we say the biggest one was supposed to equal the 3 smaller ones added up?
Yes.
Something's wrong here, because look, a half plus 10 half plus 16 half. Wait, a half plus 10 half plus 16 half equals 17 and a half? I'm not buying it. How about this one? 21 and a half equals 11 plus 5 plus, this one works. This one, something's wrong, so we must have made an arithmetic or algebra mistake or something, because the 3 smaller ones are supposed to add up to the biggest one. Let's look back at the algebra there. A subtracts out, so I have 2A on this side. 17.
17 minus
oops.
26.
Oops, 17 minus 26 is not 1, it's negative 9. So A equals negative 9 halves, but I think we're not allowing negatives, so forget about that possibility. We still do have a record with 9 steps, although we have to have fractions now. Can we fix it up somehow so that there's something that also lasts 9 steps but doesn't have any fractions in it?
Subtract 1 half for everything.
Subtract 1 half for everything. Will that still work? I think the problem is if we, it'll still work in terms of lasting, oh wait, does this last 9 steps or 8 steps? I don't even know.
9 steps. Yeah, 9 steps.
You sure? But wait, can we just check that?
7 steps. That says 8 steps.
That's still 8 steps, right? But
8 steps.
it's the correct 8-step one to be work backwardable.
No, didn't we get that one from 17-10-6-1?
Oh, okay.
Yeah, and
So it's
then
like steps.
No, 17-10-6-1 is 7 steps. So you got 17-10-6-1 from the static for 5-16,
Uh-oh.
6 steps.
So you're saying I'm off by 1 in my counting of steps here?
Yes.
7, 4, 5, 16, which is 6. So this one's still only 7. It's just this was the smart 7. So that there was one before it that would last 8. Is that what you're saying?
Yes.
And then not only does this one last 8, but this is the right one that lasts 8, so that there'll be something before it that'll last 9. Because 4.5 plus 5.5 plus 9.5 equals 21.5, so there is something that comes before it. Okay, so we're still only up to 8 steps. Okay, so if we took away a half from each of them, I agree, it would still last 8 steps, at least I think it would. Maybe for a more compact way of writing these, so we can check. If we took away a half from everybody, we'd have 21, 11, 5, 4. And then this would be 10 in between those two, 6, 1, 17. Oh yeah, that is what we had, okay. And then that would be 4, 5, 16, 7. Oh yeah, and then we know we've got 6 more steps to go. Okay, can we subtract? I'm subtracting right here. 4, 5.
No, it should be 10 to 16. 11 minus 1.
11 minus 1 is 10. Is that what you're telling me?
Yeah.
11 minus 1 is 10?
10 to 16 is what we have.
Okay, good. 8, 4, 4, 8, 4, 0, 4, 0, 4, 4, 4, 4, 0, 0, 0, 0. So that lasts 1, 2, 3, 4, 5, 6, 7, 8 steps. Okay, good. But the problem is if I take away half like this, that one's not work backwardable anymore. Because we don't have the 3 smallest ones adding up to equal the biggest one. Whereas here, we did have the 3 smallest ones adding up to the biggest one. So taking away a half is okay in terms of lasting 8 steps, but not in terms of continuing the process so we can keep working backwards. So is there another way we can fix this up to get rid of the fractions?
Could we multiply by 2?
How about if we multiply by 2? Let's see, so if we double everybody,
Then everything in this world would double. Every
just like here, we could, if we added a half to all of these, that actually just doesn't matter, because when we subtract them, it's still 10 apart if we add a half to everybody. But if we doubled everybody up here,
everything else
we would double these, which would double these, which would double these, which would double these, but it'd still take the same number of steps to get all zeros. You just have double the thing in every step.
And you can't double zeros, so, well, if you do, you just get
You
zeros.
just get a 0. Okay, so we can add or subtract from everybody, and it goes to last the same amount of time, the same number of steps. Or we could multiply everybody, and then it both lasts the same number of steps and has the same working backwards patterns too.
It's work backward. Or work backward.
Right. Or more specifically, it's work backwardable if it was before multiplying.
Right.
Okay. Okay, so maybe instead of 21.5, 11.5, 5.5, 4.5, we really want 43, 23, 11, 9. So it's kind of interesting. Each step we've worked backwards has required something a little bit new. So first we just picked these 4 completely guesswork numbers.
It happened to work. And
That one happened to work, and we got the one that came before it right away. Namely this one right here, 1, 8, 12, 17. But then we got stuck, we couldn't work backwards, and we realized if we fiddled, if we chose this 7-step one instead, I shouldn't really have a line there, I should just go 7 steps with all the rest. Okay. If I chose this one instead of one of these, then I could work backwards to 8 steps, and we got this as the only solution there. But now we've learned about adding and subtracting or multiplying, we can get this one. So we needed to learn something new for each next step we were going to get.
Let's hope the next step is the next one.
Let's hope the next one doesn't get any harder, huh?
No, we came up with the 40, we came up with the doubling thing before you're actually trying to figure out what the sequence is. Because the equations over there, so 42 plus 2.
Right.
So actually got that.
Okay, so we have 43, 23, 11, 19 now. So our equations are going to be either a plus 43 equals, the other one's added up, a plus 43, a plus 20. Wait a minute. What am I doing? Maybe I should draw my picture so I don't get confused. Okay. Let's see, we have 43, 23, 11, 9.
Isn't this the problem on the back of your shirt?
Yep. So we have a plus 23 plus 11 more, a plus 34, a plus 43.
Yay.
Or it could be minus as I go around. And for the same reasons before, either the biggest one is the 3 smaller, we can't do the 2 and 2 thing, it just doesn't work. So a plus 43 equals a plus 34 plus a plus 23 plus a. But 34 plus 23 is more than 43, so that's going to give me a negative number for a again. Kind of seen that pattern over and over again. So we really want the minus. A equals a minus 23 plus a minus 34 plus a minus 43. I guess that's going to give us a solution, right?
It gives us 2a equals
2a equals 100?
no, 100, not.
Not 100?
It's 100. It's 100. Yeah. It's
Yeah,
100.
100. Oh, nice. A is 50. Okay. So it looks like things are going really smoothly here. We got 50 minus 23 is 27, 16, 7. Looks good to me. Okay, so let's see a new record. 50, 27, 16, 7. 9 steps. And not only is it 9 steps, but it's backwardable. There should be another one before this, right?
Is
Okay.
there always a backwardable solution?
So far, let's do it again. I want to get 100 steps. Okay, so either at some point we'll get bored and figure out a reason why it's always worked backwardable, or at some point we'll run into a dead end where we can't work backwards anymore.
Well, it should always be work backwardable because we always have the equation a equals a minus b plus a minus c plus a minus d. And
That's
it
true.
always gives a positive solution for a,
That's true.
meaning it's always work backwardable.
Can I tell you what I think might go wrong with that argument? What if we got a positive solution for A, but it was, let's say, 25 instead of 50 in this example? Then A would be 25,
Right.
and then I have 4, and then I have a negative number and a negative number. So I have to not only make sure that I have a positive solution, but that
It has to be.
the positive solution has to be bigger than this number. Bigger than or
It
equal
has to
to.
be greater than or equal to
Yeah.
the biggest difference.
Yeah. So in this one, I'll get the same thing. If I start with my A, I guess I'll start with it here. Maybe they'll call it a different letter to avoid confusion. It would be B minus 27, and B minus 27 plus 16 is 43, B minus 50. So you have B equals B minus 27 plus B minus 43 plus B minus 50. So you get 2B equals, let's see, 60, 70, 120. So B is 60 now. That seems fine. So my next solution is 60. 60 minus 27 is 33. 60 minus 43 is 17. 60 minus 50 is 10. Okay. 60, 33, 17, 10. Okay, let's go back another step. Is this just really always going to work, or we're always going to get not only a positive solution, but one that's bigger than this number? Well, what are we going to get now? I'll put C minus 33, C minus 50, C minus 60. So I'm going to get C equals C minus 33 plus C minus 50 plus C minus 60 is looking pretty good, isn't it? So I get 2C equals,
That's just 263 times 2 minus 43.
okay, if that's easier. 483 then?
Yeah, 483.
Yeah, all right. So, okay, hold on a second.
I think this goes on forever because you can also do an algebraic proof by contradictions.
Wow.
It's not that complicated.
Okay, so let's just look at what happens going forwards again. 483, 263, 143, 77. So what's going to happen from there if I start working forwards? Well, I get 220 and 120 and 66. And crazy big number, 406. Is that what I really get?
Yeah.
Okay. Do you try to make any arithmetic mistakes?
No.
But you're sure or you're not sure? You're sure I didn't make any arithmetic mistakes, or you're not sure?
Sure.
You're sure? Okay. Just one arithmetic mistake right now is going to kill the whole thing, right?
Right.
54, 340, and 186.
Agreed.
Okay. 46. Oh wait, 46. That sounds familiar. No, 43. Shucks. This is 46. I don't know. 286.
Yeah.
154. And 86. I can do that one.
Okay, you know that 20.
Wait. What did we just get there? We got, I'm going to have to write it in red right over here. We just got
Wait, we got the
286.
double. We got the double of
Right.
the 43.
154, 86, 46. We doubled it because we had the half in here a couple times, so we had to double things, right? So it looks like after 3 steps, we're back to here. So I guess this works pretty well. We just got 3 more steps.
Yep.
So if we wanted 3 more steps after that, we could just repeat this process, right? We could
And
write
we can do
down
that infinitely many times.
263 and then 483, and then the total of all 3 of these, whatever that is, and then the last number would be the total of all 3 of those, and we get even bigger. And we keep going. We copy down the 2 from there, and then the total of all 3, and then the total of all 3 of those, and we can keep going. So it looks like we could make things that last as long as we want by going that way. Okay, I think I might be supposed to stop now, so that's a pretty exciting conclusion to stop on. Maybe we should look really briefly at 2 more things. So, I don't want to waste that. Okay. Let me show you one more thing. And then we'll conclude with a little special trick you can go home and teach your parents or something. All right, so what if we started with some nice numbers like, I don't know, 1, 2, pi, 4.
Nice.
Right? How long do you think that one's going to last? Infinitely long, yeah. Sure seems
Pi
like it.
is infinitely long.
Because pi has all these crazy decimal places. Well, let's figure it out. 2 minus 1,
1.
pi minus 2.
1.1.
No, it's pi minus 2.
4 minus pi.
Okay, 4 minus pi, because 4 is more than pi.
Wait a second. Is it pi cancel?
Not yet. 4 minus 1 is
3.
3. All right. Okay, so let's do this again. 3 minus 1 is
2.
2. Which is bigger, pi minus 2 or 1?
Pi minus 2.
Yeah, pi is more than 3, right? Pi is some number between 3 and 4.
Pi minus 3.
So this is pi minus 3. How about here? How far is it between pi minus, oh boy, pi minus 2 and 4 minus pi? Which one's bigger? Let's see. This is 1 point something or other, right?
It's pi minus 2 is bigger.
And this is 4 minus 3 plus. 4 minus 3 and a bit is going to be less than 1. So this one's bigger. So this one should be pi minus 2, which is bigger, and subtract 4 minus pi. That looks like 2 pi minus 6 to me.
So it just came back.
Okay. And then how about
3 is obviously bigger than.
3 is way bigger than 4 minus pi. Okay.
So it's.
So one, right? You can make one last 1,000,000 steps if your integers are big enough. But you can't ever find anything that actually goes on forever. It'll still eventually get to all zeros. We think. We never proved that.
You can find something that can be worked backwards forever, but you can't find something that goes on forever.
With integers, you can't. We didn't prove that though. But we could prove that
There's also
if we had time.
condition.
And so then the question is, can you find something with non-integers that actually lasts forever? Okay. So if you want to spend some time working on this problem, I'm going to give you my email address, which I guess somehow is not on the handout. I don't know quite what to do with I. I think the absolute value has to be interpreted differently in that case. Okay. So I'll put my email address up here. So if you think about this problem anymore, you can find my name on the handout in a little tiny print up in the corner, but not my email address. Let's see. I'll give you this one because it's easy to remember. So feel free to send me an email about this problem. And I'm just going to give you one sort of last little puzzle that has nothing to do with the problem we've been talking about, just because I think you need something that's easy. Well, this is pretty easy to take home and show your parents, right? You can say, look at how long these numbers last. I bet you can't find numbers that last that long. Okay, anyway. Yeah. Okay, so are we ready? You need to have your hands available for this. And the grown-ups should probably practice this too. Okay, are we ready? Are you ready? Okay, so you go like this. Okay, cross your arms, put the right arm on top. Okay, right arm on top. Okay, clasp your hands together. This is called the problem-solving salute, by the way. I know it's a little funny looking. Wiggle your little fingers. Wiggle your thumbs. Wiggle your little fingers. And then you turn around. Wait. You didn't do it right. Watch carefully this time. Take your hands. Put the right hand on top. Clasp your hands together. Little fingers. Thumbs. Little fingers.
No.
Do I have strange arms or what? Here's the clue. Our big theme here from the problem-solving point of view is right here. So now solve the problem that I just gave you. What's the end? End like this with your right thumb on top, by the way, it makes it a lot easier.
Oh.
Where were you at the step before that?
Turn right.
Turned around like this.
Wait, what?
So you can work backwards all the way to the beginning. And if you practice your working backwards enough, you'll see that the trick is that when you put your hands together, the natural thing to do is for your thumbs to go out like this. But if you do the working backwards, what you'll see is this thumb can go the way that feels good, but your left thumb has to go the incredibly awkward, painful way. when you put them together.
So don't do it for too long.
Right, so you cross, flip it, with your right hand going the way that feels nice and comfortable, and your left hand going the horrible, painful way. And then you'll be in position to do this. Does this make sense? Let's practice one more time just so we can see that everybody's got it. Okay, arms up, cross, put them together. Right hand going the normal way, left hand going the painful way. Right hand goes normal, left hand goes painful. They both have to turn close to 180 degrees. Whatever silly wiggling you want to insert at this step, and then done. Okay? So thanks for coming. I think there's a little break. There are probably some snacks back in the main room. And then you can choose another session for the following block of time. So thanks for coming.
Thank you.
Thank you.
Sure.